demonstration here. What I'm going to do is I'm going to dissolve a couple of salts. Okay, first salt I'm going to dissolve is going to be lead nitrate. And so if I look at my nitrates, I see that my nitrates are always soluble. What does that mean? It means that in water the ions are free, available, they're not stuck together. So if I have lead nitrate, notice the 2, because lead is +2, each nitrate is -1. You get that from table F or table E. All right, so obviously I got lead nitrate. So taking lead nitrate and some water, okay, just gonna, there it is, there's the salt, okay, a little bit of Vasa, water, okay, and I stir to my heart's content. Because it's soluble, these solids will do what? Ooh, getting too close and personal. What will these solids do? Solids will mix, not mixing now. The solid should what? Dissolve, which means I'm making a homogeneous mixture. Okay? All right, cool beans. It's almost there. Definitely a lot less solid than there was, right? Okay, now I'm going to put that in here. And there is my test tube of lead nitrate. All right, well, I've got a crystal of potassium iodide. Woo, where are we? There it is, nice big lump crystal. Light doesn't get through it because the positive and negatives are orientated like this. Woo! Okay, so light doesn't get through it, positives and negatives. So party people, lead iodide. Let's go there. Okay, that's Ki. Ki solid, but can it be aqueous? Is it soluble? Will it break apart into what? Free ions. Will water compete for these charges and pull these ions in water? Because you need to have these free ions in order to maintain electrical neutrality in a salt bridge, or be there to act as the oxidizing agent. Okay, so potassium is a group 1 ion, always soluble. So it's remember, it breaks apart into K plus and I negative. So I negative is a halide. Remember halogens? Remember from our summer? Halogens are group 17. They're all -1, so that I is normally soluble. Look at the exception though. With lead, it's not soluble. So when I add lead nitrate to potassium iodide, okay, this was a double replacement reaction that we did over the summer and or you did in Regents chemistry. Bottom line is, since the nitrate does what? And the K plus are always what? They don't do anything. So what's going to happen when I pour these together, the Pb plus 2 plus I negative, and how many would I need to make a neutral compound? 2 of them, right? Because one is -1, one is +1. So what you're going to make is PbI2. And what would be the phase? These are aqueous, these are free because water competed with those charges. What's this going to make? Solid. I'm going to make a precipitate. And if a precipitate is forming, based on my solubility rules, what's happening to the amount of lead ions and iodide ions in solution? What's happening to the number of free ions? Decreasing. You're taking out the free ions, right? They're coming together to form a crystal. So you've got these free ions, right? Maybe in my hand. Ah. And of course, if they're going to what? Stick together in water, because water can't compete with those charges, they make a crystal. Okay? So, back to reality here. I've got my Ki, We just said it was soluble for two reasons, group 1 ions, and what else? And halides are soluble. So pour this in. And notice water's competing with those charges very well, because what's happened to that solid? Yeah, those ions are now free. And now I've got a dissolved, homogeneous aqueous solution of K+. We may write Ki, aqueous, but that's a lie. It's a Kardashian wedding, right? They're not really together. It's K+ ions. All right, so now I'm free. And so let's do this. So now I'm going to add the K+ ions, but more importantly, the iodine ions in here. And I'm going to add them to the what in here? The lead, and I'm going to precipitate. So let's do that. Ready? 1, 2, 3. Did I make a precipitate? Did I make a precipitate? How do I know I made a precipitate? Okay, color changed, but I can't see through the solution. I can see through an aqueous solution because the individual ions cannot what? Are so small compared to the wavelengths. But nothing gets through what? Solid. Just so happens lead iodine is a very famous, okay, yellow precipitate that used to use in paints, okay, until I realized that not a good idea, especially in homes. Kids would start eating them, okay, because it's, hey, they must be flavored. And having lead into your body is not a good idea. It's a heavy metal, can mess with neurological problems. So there's an example, all right? And this precipitation may give you problems in a battery if you're lowering the wrong ions. This looks a little different than what you just saw a few minutes ago, because the solids, okay, the precipitate being more dense than the solution eventually settle to the bottom. So the precipitate, the solids are not at the bottom. What you should recognize is that what's left in the solution is what's spectating. And what is spectating? Well, the nitrates from the lead. Remember, the lead nitrate delivered the lead ions. So there's still nitrate. Yeah, so in solution we still have water. You've got potassium ions and nitrate ions. And in another course you may write KNO3 as the product, but really it's K+ aqueous and NO3-. They don't come together as you may have written in a double replacement reaction.